Right. Well, I need to make the move that down so it's not right in the front. Okay. Anyway, hello everyone. Yes, Jackson, nearly there. I was 490. Where was I? 495 subscriptions last time I checked. Yeah, we can do it. Thank you for everyone's vote of confidence. Anyway, let's get on with this. So, good evening and hello. This is my tuition session. It is Tuesday at 6 p.m. So the regulars are all here. I can see you're all typing your message in. Oop, point the other way. See you're all typing your message in there. Hello, Lex. Hello, good to see you. If you're new here, this is your first time. Hi, Joe. If this is your first time here and you've not been here before, then the way this works is we're going to go through some questions together. You can type your answers into the Discord chat, and then we can have a bit of a discussion about those answers, or you can ask questions if there's things you're not sure of, and that's how things can go. What's going on there on my Discord? Anyway, that's how things can go on today. So the plan for today is to look at the rest of those questions we hadn't quite finished last time on space. And then I want to move on to gravitational fields, which is related to space. Mainly so the A-level students don't feel left out. But it's also good for the GCSE students to see where their work on vectors that they possibly are working on at the moment. I know that with my class of year 10s, we're working on vectors at the moment. So it'll be good for them to see where vectors gets used a bit further down the line in physics. So even if the context of gravitational fields is a little bit, forgive the pun, alien, you're not going to necessarily need it in GCSE level. The skills of adding vectors together you will need. And so that's why I think it's worth bringing it in at this stage. So Dvorak as well. Hello, it's good to see you there. I know, Jonathan, I'm basically a comedian. Right, so let me switch across to... There we go, to the questions we were looking at last time. This is the last question we looked at. Reminder, I had to seek permission to use these questions. These are the OCR questions. AQA and EdXL, unfortunately, were unwilling to allow me to use their questions, but OCR was very generous and said that I was allowed to use their questions as long as a few conditions were met. Firstly, that I broadcast the question in its entirety. Don't cut things out or modify the question. Secondly, that I make it abundantly clear that OCR does not endorse my solutions. They have not seen my solutions. Nothing I'm doing right now is supported or endorsed by OCR. And the third thing is that I have to say where the questions come from. So the question we were looking at, I have to point the other way this time. The questions we were looking at last time were these questions, OCR, GCSE 9-1, the Physics B Breadth in Physics paper, the sample question paper. I think Physics B is the 21st century science course if you're studying that. But even if you're not, there's so much overlap between the exam boards that it's not a problem if this isn't the specific exam board that you look at. Okay, with that said, let's get on. So we started with this question last time. We didn't quite finish it. So just to recap, we were looking at the changing ideas about our universe. Scientists suggested the universe was not changing in size. Explain the effect gravity would have on a universe that's not changing in size. We had a good discussion about that. Gravity trying to pull things together. But if the universe is not changing in size, then what's the effect of gravity? And I don't think we came to a conclusion about that, but I wasn't willing to look at the mark scheme because I don't want to end up just teaching OCR physics. So we talked about what gravity... If you want to see that, look at last week's session. And I can't remember if we came to a conclusion in the end. Part B, about this time, Edward Hubble noticed redshift. Explain what's meant by redshift. We gave a good description about what redshift was. I can't remember who that was. I think that was Pranav last week. He gave a great description of what redshift was. Explain what's meant by it and how this shows galaxies are moving away from each other. Oh, Sanskar. Hello, Sanskar. So, yes, we had a discussion about those two things there. And then this is where we finished up. And I said, look, we're out of time. We have to go. Which was describing the trend shown in figure 8.1, which is these graphs here. And explain how the data provided evidence which led to the Big Bang model. And so we talked about how the reciprocal of the gradient is the same for all points and it can be interpreted as the time since all of those galaxies were in the same location, moving apart from each other since that point in time. So then the question goes on, from the graphs, astronomers can work out the age of the universe. Explain how the data can be used to calculate the age of the universe. I think I've kind of already done that. Assume the speeds of galaxies have remained reasonably constant over time. So I think I've done that one, so I'm going to move on from that question. Suggest 2 reasons why present-day estimates of the age of the universe are more valid. So let's see what you come up with. Now it's your chance, your turn, to put some answers down there into the Discord box that you can see. Now, if you're watching this on YouTube and you're thinking, where's that Discord box? Where am I typing this? Look in the description of this video and you'll see a link. If you click that link, you get yourself added to this Discord server, and the link should take you to this Discord channel so that you can type below. So what I want to know is, answer to this question, suggest 2 reasons why present-day estimates of the age of the universe are more valid than Hubble's initial values. Hubble's initial values determined by these 2 graphs, 1929 and 1931 there. So suggest 2 reasons why present-day estimates of the age of the universe are more valid. I love it. Right now it just says on Discord there, several people are typing. That's reassuring. Suggest 2 reasons why present-day estimates of the age of the universe are more valid than Hubble's initial values. So Jonathan's given us an answer there, which is more research has been done and validated by more scientists. So the more research has been done is perhaps a little bit vague, but the idea that it's been validated by more scientists, I think, is definitely a point that's worth mentioning it. The 2 initial studies that we're talking about here were done by Hubble and Humason, is that? I think that's Humason. So you need somebody else. You need another scientist to verify some of that data. So I would think that's a point worth making. So Lex has said greater accuracy of observation. Instruments and more peer-reviewed research. So I'm glad you mentioned more peer-reviewed research. Yes. So the research that was published was originally peer-reviewed anyway, Lex. But the more peer-reviewed research could come from 2 places. Either Hubble did more research himself, which he undoubtedly did, but also other people did it as well and found results that corroborated. So when we say more peer-reviewed research, there's 2 dimensions to that. There's more research by Hubble, but there's also other scientists verifying what was observed, checking that the results were both reproducible and repeatable, 2 slightly different things. If they're reproducible, following exactly the same technique, the same procedure, you can get the same results. If they're repeatable, then you can get the same results via some other scientific process as well. So Pranav said present-day estimates is more correlated. You've mentioned R² value closer to 1. So presumably you're talking there about the product correlation coefficient, the Pearson PMCC, product moment correlation coefficient, the PMCC. The product moment correlation coefficient is a quantity that's used by A-level maths students, we don't tend to talk about it so much in physics, to quantify how well correlated two variables are. How straight, not how straight the line is, how close to the line the points are. So GCSE students wondering what Pranav was talking about when he said R squared, he's talking about Pearson product moment correlation coefficient, a quantity that appears in A-level mathematics for statistics, but it doesn't actually appear in A-level physics. And then when I, in my first year at university, used product moment correlation coefficient, when I analysed the errors, the uncertainties in a practical, my supervisor, my lab supervisor, raised an eyebrow and wondered what on earth I was talking about. So I think it's only mathematicians that get very excited about PMCC. It doesn't seem to be physicists. And then Pranav goes on to say the data is taken from a larger set of galaxies. Yes, but there's more. A larger distances from Earth. There's the golden nugget. A larger range of values. We extend the data we've got beyond that range. So a larger range of values, Pranav. Absolutely right. So Dvorak says better telescopes. Yes. I mean, Hubble's telescope, well, I shouldn't call it Hubble's telescope because that could get confusing. The telescopes that Hubble used were on the ground. And so there are various reasons why the data you would get from them wouldn't be perfect. The colours could be distorted by Earth's atmosphere, for example. But if you can get a telescope in space, which we have done since, then you don't have those atmospheric distortions. So you're going to get more accurate measurements of the wavelengths of light that are emitted from those stars. Now, it shouldn't really matter, but it probably reduces, well, it will reduce the uncertainty in any measurements you take if you don't have the shimmering atmosphere to contend with. You said to take more accurate measurements of the redshift, so velocity and distance. Yep, fine, I agree with that. Make better estimate for the age, I like that. Antonio, better telescopes, more precise measurements is, I'm afraid, it's just too vague. It's just too vague. So better telescopes, yes, but how are they better? Why are they better? We're suggesting two reasons, so we're going to want a bit more meat to our answer. So Joe 11 says, could it be worked out the speed of light and redshift? Was Einstein part of the estimation? So, yeah, when this was done, so this was back in 1929, theory of special relativity was known about. In 1931. So redshift was understood using relativity as it was. So I don't think I'd put that down as an answer, Joe. No. Einstein's theory of special relativity, I think, was 1905. Could be wrong with that. Might be a little bit later, but it was certainly before 1929. So I don't think that would be the answer there. So Dvorak says redshift allows you to find the recession velocity of distant galaxies. Correct. That's how fast they're moving away from us, which requires knowledge of the speed of light. It does. That was already known about, though. Speed of light was estimated by Fizeau already with Fizeau's apparatus. Yes, Pranav, the Hubble Space Telescope is in space named after Hubble. That's why it's named that way. So Dvorak, the speed of light was already known about. It was estimated from Fizeau's measurements, but also it was predicted from Maxwell's equations. And the two of those corroborated and gave a very, very similar number for the speed of light. So it was already known about. But I think you've got there. So extend the range of data and have other scientists validating the results by proving that they're repeatable as well as reproducible. It's no point just reproducing them because there could have been something within the experimental method that gave rise to those results. They have to be repeatable as well as reproducible. Okay, so I think we got some mileage out of that question. I think that was worth finishing off. Are there any more questions about that before we move on to the next one? If not, A, B, B or C apparently. This is a sample question paper, so it appears as though there are some typos in it. I'm going to make an executive decision here and rename some of these. A, B, I'm going to call this one C and this one D. Again, OCR does not endorse any of my slander about their papers. I'm sure they did intend it to say A, B, B, and C. Anyway, what do you think the answer is? B1. Well, Jackson, I have been known when making multiple choice papers, I have been known to deliberately make every answer the same letter just because it messes with students' heads. They just don't believe their answers. Oh, hello, James. I didn't see you here. It's good to see you. I think you're a new name. So yes, B1. Yeah, so dust and gas pulled together by gravity leading to a fusion reaction. I think I'm happy with that. I think we can say it's definitely nothing to do with fission, the splitting of one large nucleus into two lighter nuclei. Nothing to do with that. And the idea of gas being pushed together by gravity, I mean, I'm not really happy with the idea of pulled together, but it's a colloquialism, and I think we can go with that. So let's put B1, just to be facetious. Okay, so this one's going to require a bit of writing. Question 19. So question 19 is worth 6 marks. So there's a lot of writing here. So I'll be interested to see what you put as your answer. Scientists collect evidence from the universe to develop theories that explain their observations. Fine. The diagram shows 3 absorption spectra. Now, if you don't know what an absorption spectrum is, let me know. I can tell you. If you all know what it is, I won't bother. But if anyone's not quite sure, let me know and I'll tell you. It says the white arrows show the relative positions of the same band. So you can see that the pattern here has been sort of moved, shifted. We've got 2 lines close together, bit of a gap, a line, bit of a gap, a line, bit more of a gap, a line. And we've got the same thing here. 2 close together, bit of a gap, a line, bit more of a gap, a line, bit more of a gap, a line. Yeah, no worries, Jackson. I'm happy to give you an explanation. And we've got the same thing here. 2 of them close together, bit of a gap, a line, bit of a gap, a line, bit of a bigger gap and a line. So you can see it's the same sort of fingerprint that's just been moved around. Let's just delete my little nonsense I've written there. So I'll talk about absorption spectrum in a second while people are typing their answer. The white arrows show the relative... I've just read that bit. And so using your knowledge of redshift, describe how the information in the diagram supports the idea of the Big Bang model. So we've got a nearby star, a nearby galaxy, and a distant galaxy. So while you're typing your answer, I'm just going to answer the question of what is an absorption spectrum. If I take a gas and I get it excited, so I either heat it up very much or I put a big electric potential across it, I get it excited, then as the atoms in that gas de-excite, they emit characteristic colours. Now, you might have met this idea in chemistry with flame tests. Certain elements, when you place them into a flame, because the atoms in those elements get excited, when they de-excite, they emit light of very particular colours, very particular wavelengths. But it works in reverse. So just like there are certain colours of light that can be emitted by excited atoms of a particular element, if I take just that particular element and I pass white light through it, certain colours of light can be absorbed by that gas as well. So you would have a rainbow coloured spectrum, much like you can see just below me, that little background to the Discord chat, that lovely red through to purple rainbow spectrum. But certain colours will be missing because the light is absorbed by the gas. In the case of stars, mostly hydrogen, will absorb certain colours. And it turns out the colours correspond. So if I take hydrogen and I get it excited, it will glow, mostly red. We get this beautiful red colour coming out of it, and some other colours as well. And if I take hydrogen gas and I pass white light through it, then light is absorbed, and the main colour that's absorbed is red. The main colour that's absorbed by that hydrogen. So those absorption lines, these dark lines you see on this picture, correspond to the colors of light that the atoms of that element absorb. They are also the colors of light that the atoms of that element emit when the atom is excited. It's actually the same sort of quantum physics driving both processes. What you can't see, because it's a black and white picture, this is from OCR. I haven't photocopied it and lost the color. This is from OCR. I'm not allowed to modify it. A real spectrum has the colors. So red, orange, yellow, green, blue, purple. And then just black lines missing from it. So I hope that's helpful. I can see there's plenty of people typing away whilst I was reading that, whilst I was talking about that. Oh, Jackson's the first to get his answer in. So let's have a read. The distant galaxy is the furthest away. Correct? That's what the distant galaxy means. So the black lines, not sure what to call them. Yeah, just call them black lines. We can call them absorption lines, but just call them black lines. If you want to call them absorption lines, even better, but I don't think it really matters. So the black lines are furthest along the graph, meaning that they are moving away faster. So the black lines are moving away faster. You've used the word they, which is a little bit ambiguous. I'm not sure what you're talking about. So it supports the fact they all originated from the same point and are moving away from each other, expanding. This is a complete guess, so I might be wrong. No, there's a lot of good things in there. You had the right idea that the galaxies are moving away, the distant galaxies. What you didn't mention, oh, you did mention, sorry, that the distant galaxies are moving faster. That's critical. You've got to have that in your answer, and you had that. Okay, yes, so the galaxies are moving faster. Yeah, I like that, yeah. So Freya said, supports the model because it shows that all galaxies are moving away from each other. We know this because we can see galaxies red shifting. That's not quite true though, Freya, because Andromeda's moving towards us. It just happens to be a very nearby galaxy. Looking at the picture here, probably nearer than the galaxy they've labelled as nearby galaxy in that awful font. Seriously, what were they thinking? Nearby galaxy? Why have they written it in that horrible script? So, Joe, as the distance from the observation point increases, okay, so this is the distance to the galaxy or the star to us increases, the light absorbed has a longer wavelength. Well, all of the wavelengths are emitted. The idea is that they've been shifted. So what we now see as red might have been infrared, but there was still infrared there. So what we now see as infrared probably was microwaves, but there's still microwaves there. So what we now see as microwaves was radio waves and so on. So as longer wavelengths, yeah. So it's more that they've all been shifted along rather than that it's just the wavelengths have all increased. They've all been shifted along. It's due to the galaxies moving away from us, which can be explained by, whoops, it's gone off the side of my screen. I'm going to have to read it off my phone. It can be explained by space expanding. Implies there was a point in time in the past when galaxies were close together. They moved away from each other. So the end bit there is okay. The end bit there is okay. Yeah, not a bad answer, Joe. So Dvorak, you say, in the diagram, the more distant galaxies have dark bands towards the red end. This shows that the further away object is, the more light from it is red shifted. But yeah, okay, so you haven't defined redshift. The redshift indicates the object is moving away. The greater the redshift, the faster it's moving away. Perfect. Glad you said that, Dvorak. The fact that more distant galaxies have more redshift indicates the space between them is expanding. The point is, the further away they are, the faster they're moving, which implies that everything is moving away from everything else at the same speed. It's a bit difficult to get your head around, but the old expanding balloon model can help explain that. This supports the Big Bang theory as it indicates the universe was once small before expanding. Yeah, okay. I like that. Very, very small. Very, very concentrated. So Wombat says redshift where the wavelength of light increases towards the red end of the spectrum. Yeah, I mean, the whole spectrum is shifted towards the red end. The whole way, all of the wavelengths are increased. All of them. All of the wavelengths are increased. So the wavelength of the black lines has increased. That's why the black lines have moved, because all of the wavelengths have increased. Oh, wow, there's loads of answers. Okay, so redshifted colors. Yeah, I like your answer. The further away the galaxies, the more redshifted they are. A nearby galaxy compared to a star. What's the big? So you missed a key point there about the star versus the nearby galaxy, but we'll come to that. Galaxies are moving further away, therefore once was a point back in time. Yep, so I like the way you concluded that. James, you said the absorption spectra for the two galaxies have both undergone redshift because they're moving away from us. Distant galaxy moving away from us faster rate. Yep, that's a good answer. Yep, it's a good answer there. So a few key things here. Some exam technique for you. Oh, it's another answer from Pranav. I wouldn't start talking about what's going on at the blue end, Pranav. I wouldn't talk about that. I'd concentrate on the shift towards the red end. So here's some exam technique for you. Whenever you see a technical term, define it. This is true for GCSE and for A-level physics students. Whenever you see a technical term, define it. So we have seen absorption spectra. We need to define what that means. We need to tell the examiner that we know what an absorption spectrum, singular, is. And therefore we know what absorption spectra, plural, are. So then we've got redshift. That's another technical term that demands definition. We've then got the idea of galaxies and stars. What's the significance? Why in this question is it talks about a nearby galaxy and a star? So we're going to have to unpick the relevance of that. Using a knowledge of redshift, describe how the information in the diagram supports the idea of the Big Bang model. We're going to have to define the Big Bang model. So if you look at what I've underlined there, there's 1, 2, 3, 4 things. It's worth 6 marks. We've already identified 4 things to talk about before we've even written the answer. Hello. We've detected 1 new update for Kaspersky security. Go away. Now is not the time. So let's start off by absorption spectra. So we can say, and I'm going to do my best handwriting now, an absorption spectrum is, how would I describe it? Or is formed, is produced when, this is some atrocious handwriting, when white light passes through a gas and certain wavelengths are absorbed. None of you mentioned that. It's really not, Pranav, but thank you. So none of you mentioned that, and it's absolutely critical. So certain wavelengths. What wavelengths? I now need to go further. It's 6 marks. I need to go further. What wavelengths? So we can say stars contain mostly hydrogen. So the absorption spectrum of stars and galaxies, I'm going to put in brackets, which contain stars, is mostly hydrogen. So the absorption spectrum, which matches or corresponds to, oh, look at that, corresponds to the emission spectrum of hydrogen. Which we can measure on Earth. And that's a key point. We know what this spectrum is supposed to look like. Which we can measure, or I'll say in the lab. Drop that out. In the lab. Okay, so if you notice, I haven't actually really answered the question yet. I'm still defining absorption spectra. Admittedly, I'm having to cram it all in. My handwriting isn't very good because I'm writing on one of these tablets at a funny angle. Admittedly, you know, I've already used half my space, but my handwriting would be about half the size if it was on paper and far neater. So bear that in mind. So right, well, I'm going to say this. I'm going to actually say it. So we know what the absorption spectrum should look like. Okay, so now I'm saying that what I can now do is compare it to the absorption spectrum we've got. But before I do that, no, I'll do that now. I'll do that now. So we can say the absorption spectrum. So what I'm now doing is defining redshift. The absorption spectrum, spectra, plural, for more distant galaxies is shifted. I'm not going to use the word shifted because it's in the definition of the word redshift. So I'm going to have to think of a different way of describing this. So the absorption spectrum then has black lines with larger wavelengths. I like your suggestion, Pranav. Oh, why have I put an apostrophe? It's plural. Oh, what have I just rubbed out? Distant galaxies. Black lines with larger wavelengths. Okay. I'm running out of space, so I might just have to verbalize this rather than writing it. I've nearly defined redshift. What I might say is the more distant the galaxy, so more distant, more redshift. I've defined redshift. Then what I need to do is say why redshift happens. So I need to talk about how as the distance between the source and the observer increases, the waves are stretched out. There's another piece of information. I'm defining redshift. I can then say that the faster that recessional velocity, the more the waves are stretched out. And therefore, the more the black lines move towards the red end of the spectrum. So this end over here is red. This end over here is blue. So now I've defined what redshift is. I've talked about what's happening. I can now tie it to what we're seeing. So do some elements have absorption lines in the infrared or ultraviolet parts of the spectrum? Ultraviolet, yes. Infrared, yes. That could appear in the absorption spectrum when red or blue shift occurs? Yes. James, although I can't think of a specific example, yes. The answer is correct, yeah. So why have we got a star in nearby galaxies? Should we unpick this bit now? It's because the only stars, with the exception of supernovae, which outshine their parent galaxy, the only stars that we can observe are in our galaxy. So there's a bit of astronomy knowledge in there that you needed to have. So where it says star, we are looking at stars that are not moving away from us. Our galaxy is not appreciably expanding. Although I'm sure it is, because of the gravitational force between the stars, it's also contracting, so the galaxy just stays the size it is. So when we look at the star, what we're looking at, yeah, exactly, Jackson. The star is the closest, has the least redshift. It is moving the slowest away from us. Exactly. So we know the star is the closest. Absolutely right. Then nearby galaxy is outside our galaxy. It has to be. It's not Andromeda because Andromeda is blue shifted. So that nearby galaxy is some other galaxy nearby. So we would say the nearby galaxy is further away from us than the star because the star is in our own galaxy. The distant galaxy is even further away from the nearby galaxy, and you can see that the corresponding dark lines are shifted towards the red end. Say in your answer that the red end is the right-hand side of this spectrum because it's black and white. I wonder if that's deliberate so that you can get a mark for pointing it out. And you know what? I've run out of room, so I'm going to put my hand up in an exam and I'm going to say, excuse me, sir, excuse me, miss, could I have another piece of paper, please? I'm not going to write in the margins. I'm not going to write on a blank piece of paper somewhere in the back of the paper where it says this page is left blank. Leave it blank. Ask for additional paper if you need it. I would probably need it, but then I write far too much. And then finally, it says, use your knowledge of redshift. I've demonstrated my knowledge of redshift. I know what redshift is. To describe how the information in the diagram supports the idea of the Big Bang model. Now I need to define the Big Bang model. The Big Bang model is the idea that all the matter in the universe was condensed in a very, very small volume and then expanded from each other. If that is true, then everything is moving away from everything else. And therefore, things that are farther away have to be moving faster to still be moving away from the nearby galaxy. Look, the distant galaxy has to be also moving away from the nearby galaxy. Therefore, the distant galaxy has to be moving faster from our perspective to the nearby galaxy. Otherwise, these two wouldn't be moving away from each other. They are. That's the idea of the Big Bang theory, which I've just defined, and I'll have 6 marks. Thank you very much, examiner. There's a lot in that, a tremendous amount, but the most important thing I want you to get out of that is the exam technique. The likelihood is you would not write all that waffle that I just said, but you probably wouldn't need to get 6 marks. But follow the recipe. Define your keywords and try to spot little tricks that the examiner is using. If there are any questions, please do ask them. I'm ashamed of my handwriting. I think next time I'll write slower, try to make it neater. Just to prove that I can. No questions? Okay. So, same paper as before. Remember, this is the sample question paper, paper 4 from Physics A, which I think is the Gateway Physics course. It says, state 2 features of a satellite in polar orbit and suggest a use for a satellite in polar orbit. Go. See what you come up with. It will not be a GPS satellite, Pranav. So 2 features of a satellite in polar orbit. Basically, it's saying define polar orbit. Honestly, I tell my students this all the time. Sometimes they believe me, sometimes they don't. If you just define the words that you're given, you get marks. This is just a dictionary exercise, memorizing definitions. So Dvorak has said it doesn't stay over the same part of the Earth at all times. Well, you've said what it doesn't do. I'm more interested in what it does do. Same radius? Yes, Wombat. I like that. Same speed? Yes. Another way of saying that might be that it travels in a circular path. Traveling over both poles? Yes. And used in communication not, I mean, maybe Wombat, but probably not the best use of it, because then you'd have to track where the satellite is with your communication dish. So probably not for communication. Not unless you're trying to hide your communication somehow. So Ben says, takes the satellite over both of the planet's poles. Like it. Travel relatively close to the planet. Yeah, actually, it turns out that they tend to, but they don't have to, but they tend to. Mainly because there's some sort of international negotiation about how high up the satellites can go, where they can go. But yeah, so over the poles, I think we need to state that. Circular path, Pranav, I think we need to have that, yeah. A weather satellite is a good answer there. Weather tracking, yes. Wombat and Pranav, you've got that. Weather tracking, very good. Weather satellite, yeah, absolutely. And as Dvorak says, it will be over it says every part of the Earth. Yeah, I mean, you'll be able to take photographs of every part of the Earth at some point within one Earth rotation. Why might that be useful? Why might it be useful to have something in space that is over every part of the Earth's surface at some point? We've got weather, and that's a really good example. Can we think of any other examples? I mean, you don't really need to do that for map graphing, Pranav, but yes, I suppose so. Circular path can be used to map the Earth, yeah. So let's think about mapping for a second. Let's go back to mapping. So map graphing, or just mapping. Natural disasters is a good answer, Wombat, yeah. And that comes close to weather, doesn't it? It's the same sort of thing. Satellite imagery, yeah. Tracking weather. Moisture measurement, I suppose so, Jackson. Yeah, I haven't heard of it, but it sounds great. Oh, you've NASA's project SMAP. I like it. We've got to have some use for those satellites, don't we? Yeah, what about spies? Spying, military intelligence. You don't have to like it. I know I certainly don't, but it's a thing. Ah. I'm not sure I recognise the name Mark Rober. Vaguely. Who's Mark Rober? I'm interested now. You've piqued my interest, Jackson. Ah, okay. Otherwise known as my competition. Okay, I get it. Yeah. Interesting. I'll check it out. I mean, I'm always interested in new YouTubers, although he's not new. I'll have a look. Thank you. I've learned something. Okay, so let's move on to part B. Artificial satellite X is kept. Oh, what a probe! Curiosity, absolutely brilliant. I should talk about that helicopter on Mars at some point, but I'm not going to. Not today. So anyway, an artificial satellite is kept in a stable circular orbit around the planet by a centripetal force. Fine. Explain how the velocity of a satellite is constantly changing while the speed remains the same. It sounds like a remarkable man. Yeah, it sounds like a really remarkable man. But if I asked him to do some collaboration on something, I know what the answer would be. No. I could ask. Anyway, so, sorry. BI. This is the standard GCSE question. It could appear in any context. So today, it's appeared in the context of space. Oh, Joe, I don't know if I responded to your point about it being useful for studying global warming. Absolutely, yes. If you can see day on day, week on week, month on month, the effect of global warming, that's a very useful thing. So, yes, your answer's good there. 𝗭𝘪𝘯𝘀, that is a brilliant answer. Brilliant answer. Yeah, velocity is a vector. Of course it is. Has a direction as well as magnitude. You've defined what a vector meant. And then you've said that the direction's constantly changing even though speed is constant. That is a textbook answer. Brilliant. Well done, 𝗭𝘪𝘯𝘀. So part double I. Yep, answer's not bad, Joe. I think 𝗭𝘪𝘯𝘀's answer's better, though. Sorry. I do think 𝗭𝘭𝘪𝘯𝘀's answer's better. Okay, so part double I. Satellite is remotely controlled from Earth. Yep, James, you got it. So satellites are remotely controlled from Earth. The scientists want the satellite to move slower. What effect will this change in speed have on the height of its orbit? And explain your answer. Difficult question to answer at GCSE level. You tend to get this sort of thing appearing towards the end of the paper for that reason. So first of all, what effect will this change in speed have on the height of the orbit? What do you think? A higher orbit. Interesting. Increases the height of the orbit. Interesting. So two of you think that when you slow the satellite down, it goes further away from the Earth. Resist the gravitational attraction. You never resist it. Gravitational attraction is there. It's always there. You can't turn it off. You can't outrun it or anything like that. It would be lower in its orbit, Matthias. If you slow it down. Do you know why? I'm starting to doubt my answer, but instinct tells me that it should slow down. It should fall towards the Earth. Okay, let's draw a picture. Here's the Earth. This is an absolutely classic picture now that you're about to see. Classic picture. Let's imagine there's a big mountain. And we're on the top of this mountain with a cannon. Here's us. On the top of the mountain with a cannon. We shoot a cannonball slowly. Oops, badly drawn. Let's try it again. Cannonball hits the Earth. And so I shoot the cannonball faster. Oops. Hits the Earth. When do I shoot the cannonball faster? As I'm writing this, I think I might change my answer. Hits the Earth. Is there a speed that I can shoot the cannonball so it doesn't hit the Earth? Yeah, I'm starting to change my mind, 𝘭𝘪𝘯𝘬𝘂, actually. But I think it's a problem with the question. Because if you just slow the satellite down, I think it will fall towards the Earth. So it wouldn't be in orbit. So I think there's a problem with the question. Exactly, Matthias, yeah. So there is a problem with this question because the way it's worded, scientists want the satellite to move slower. What effect will the change in speed have on the height of its orbit? It won't orbit. It will fall towards the Earth. Exactly, 𝘭𝘪𝘯𝘬𝘂. So it's the other way around. The question's a bit back to front, and it kind of tricked me at first. If I slow it down, it will fall and it will crash into the Earth. If I want to make it go slower, then I instead must choose to increase the height of its orbit. So I'm going to dip into A-level physics just for a moment, because I know that you might enjoy this sort of thing. Centripetal force is defined as mv²/r, where v is your tangential speed, m is your mass, and r is how far away you are from the center of the circular motion. And so this is the force that must be acting inwards on you if you are moving in a circle. So if I'm moving in a... Try that again. Let's cheat. Let's draw a big circle. Going to cheat a little bit. Come on, you can do it. Okay, so then we're going to rub out a bit of this. No, not the whole thing. Just a bit there, because I want to make a big arrow. There we are. Traveling in a circle. Perfect. So if I'm traveling in a circle, then I have to have a force acting inwards. And it's conked out again. There we go. And that's going to be my centripetal force. We call it F⁻⁶ to keep it separate so we know what it is. At this point here, the mass is m, the mass that's orbiting, and the distance to the middle is r, the radius of my circular path. I'm traveling at a speed of v. The force, Fc, the centripetal force, is a gravitational force. The gravitational force is that. So if I just rub off, I'm going to try and write that a bit neater. Okay. So the little m in the equation on the right is the same as the little m in the equation on the left. It's the mass of this thing here. The big M is the mass of the planet I'm orbiting. And r² is the square of the distance between the middle of the planet I'm orbiting and my mass. This assumes circular motion. So what we can say is because the centripetal force is the gravitational force, we can equate these two equations. Now, in A-level physics, you will derive the expression for centripetal force, and I think I've got a video somewhere where I already do that. But I think I've got a video somewhere where I do exactly what I'm about to do. You equate those two forces. Because I've got a little m on both sides of the equation, I can actually cancel it. That's why the mass of the satellite doesn't matter. Okay. So now, if I rearrange this equation, I've got v², and we can multiply that by there, multiplied by r is equal to gm. So if you can see, with this equation here, if r gets bigger, this one goes up, this one has to get smaller. It has to go down. And vice versa. So whoever said that initially, who was the first person to answer that? And I said, I don't think so. Wombat, I think that was, and Dvorak. Yeah, Wombat and Dvorak. Your answer's correct, but it's not an answer to the question that I read. The question I read said that we're slowing down the satellite, in which case it spirals into the Earth. But if we want it to go slower, we can push it further away from the Earth. Now, how can we answer that with GCSE level physics? We can say that gravitational potential energy increases, so kinetic energy has to decrease. Okay, that's conservation of energy. And so gravitational potential energy increases as we get further, so higher orbit. And therefore kinetic energy decreases as we get slower. My issue is that there's a few reasons why you can't do this mathematically at GCSE level. Yeah, it's a good question, Ben. You would have to fire some sort of retro rocket to push yourself further out, which would be increasing your gravitational potential energy. So that kind of doesn't work for that argument either. Very ill-posed question. But yeah, that's how you push yourself out. And they do it all the time for the International Space Station, Ben. They kind of move it slightly to try to dodge anything that happens to be around. They don't move it a lot, but they move it slightly. And other satellites as well. But no, if you just slowed the satellite down, it wouldn't drift outwards. Not necessarily. Not unless it's already... I may be about to change my mind. Not unless it's already in an orbit, which means it's already got a speed above the escape velocity. But then when you reduce that speed, it won't be above the escape velocity and it'll fall back. No, I'm sticking with my original answer, which is the question is nonsense. It's the wrong way round. That's my answer, and I'm sticking to it, unless one of you can convince me otherwise. Again, my answers are not endorsed by OCR. I think this is the best answer you could give for a reason. And my answer would be that it would fall to the planet Earth. I would have to answer it. I couldn't not. I would have to say, if you decrease the speed of the satellite, it will fall to the Earth. But if you increase the height of the satellite, it will be in a stable orbit at a lower speed. And then for an explanation, I would use this explanation here for GCSE. Yeah, Pranav, can you see why? That's not what would happen. If I slowed a satellite down, it would fall. That's what would happen. That's what does happen. Really badly worded question. I can't see a way around it. Yeah, but the way the question's worded, what effect would this change in speed have on? That means this is the independent variable and this is the dependent variable. But it's back to front. Because the height of the orbit, well, if I decrease the speed, I wouldn't have an orbit. It'd be a smaller height, but it wouldn't be an orbit. It would just fall into the Earth. And there's your A-level physics, which you would need to answer this question in any sort of meaningful way. The height would be 0 meters. Well, not from the center of the Earth, it wouldn't. No. Oh, well. Well, do you know, we don't have time to look at fields, which is something I wanted to do. Because I spent a bit of time, probably too much time, having a good... Could the decrease in speed result in a lower orbit? No, Pranav. No, because it wouldn't be in an orbit. You'd be going below the escape velocity, so you wouldn't escape. You would fall back to Earth. Well, exactly right. Yeah, exactly right, Dvorak. Jonathan, yes, you do. I don't know why you say you can't find it on the specification, because it is there. Yeah. Oh, well, it's something for us to think about anyway. What's frustrating from the point of view of a teacher is that these sorts of questions, they come up in specimen papers. Yeah, James, exactly. But these sorts of questions, they come up in specimen papers. They also come up in real papers sometimes. Questions where the teachers end up saying, no, you can't answer this. I had one a couple of years ago where it was for the new spec for GCSE about circuits, and it was impossible to answer. And I wrote to the exam board. Well, I explained to the headmaster what the problem was, and he wrote to the exam board as the head of the centre. He has to be the one that does those communications, and said that this question is unsolvable. In order to answer it, you have to make an assumption which is so wildly not true that it caused problems. And the exam board responded, yes, we realise that, but never mind. They said no one would think that. The thing is, I know in my school we've got some of the brightest and best students in the country. They would think that because it was bad physics what was in that question. So I'm afraid sometimes this sort of thing comes up, and it is frustrating. Now, if I'm wrong, you know what? Let me know. I'm always happy to be corrected. Please let me know if I'm wrong. If I'm wrong, and if you slow a satellite down, it drifts into space, I'm happy to be corrected. Don't think that's right. Okay, so what I want to do is, because I've got a couple of minutes left, I'm just flexing now. I'm not flexing myself, am I, Pranav? I'm flexing my students, who are some of the brightest students in the country. Right. The derivation of centripetal acceleration will not be examined. Yeah, except Wombat, it specifically mentions somewhere that you have to derive. It doesn't mention it as Kepler's third law, but it is Kepler's third law. And I have seen it on a past paper. I'll dig it out for you at some point, Jonathan, if you're interested. I've seen a past paper where it said, this is an equation, derive it. So whether it says it on the spec or not, you need to do it. Derivation of centripetal acceleration usually requires some vector diagrams. It takes up a bit too much space, so that's probably why they're not going to examine that. But they will examine Kepler's third law. There we are. Thank you, Dvorak. Vindication. That completely contradicts this question. And with that note, now I've redeemed myself as someone who does know some stuff about physics. I'm going to encourage anyone who's tuning in for the first time to help me out. I'm at 495 subscribers. I really want to get to 1,000 so I can embed these videos into my website. So help me out. Share it. This was on... Exactly, Pranav. Oh, thank you, Dvorak. That's very kind of you. Thank you. Oh, that's brilliant. Look at that. Joe and Dvorak saying that I've got a few more. This is some stats for you. If you sat down and watched all of the videos on my website, apparently, according to the thing I use to scour my YouTube channel, it would take 3 days, 19 minutes and 50 seconds. And counting. I frequently get requests... Oh, all right, thanks, Dvorak. I frequently get questions from people about the astronomy GCSE videos. Yes, I will be doing more. It's just right now I'm doing assessment testing for year 11 and year 13s. So that's taking a long time, and so I don't have that much free time to record those videos at the moment. Yeah, this was on Sunday. The other thing I'm going to mention, two more things. The first thing is this. You can phase out if you want to, but I'm doing this for charity. As a rule, this one, as a rule, I don't charge for tuition. I think it should be open to everyone, regardless of your financial background. You should be able to get support. However, I do also believe in raising money for charity, and so I was asked, can I do anything? And I said, well, I can tutor physics, I guess. So if you want to get one-to-one tuition online, there's a website. Go to the link that's on Discord on the announcement channel, and you can have a look what's available there. And the last thing is, if you're a GCSE student, or if you are an A-level student who's in year 12 and you're thinking to yourself, do you know what? I made a bit of a rocky start. There is a GCSE to A-level physics bridging course that I'm going to offer. It's a week long. It's 5 days. There will be homework that you have to do each night. So it's a big course, and you're getting all that for £10. This is a suggested cost because, again, if you can't afford it, fine. But I have to pay quite a lot of money to renew my website hosting, which is with WordPress. And if I want to embed the live videos and the Discord, it's something like about £260 I have to pay them. So what I could do with is, rather than me putting my hand in my own pocket again, if somebody, if people are doing the GCSE course and they think, I want to do A-level physics, I want to make a good start, then I'm offering this course. If you want to do it but you can't afford it, let me know. You could do it anyway, because that's the kind of guy I am. Thank you very much, everyone, and I really hope this has been useful. I think we learned a lot today. We're doing gas laws next week. So make sure you tell all your friends, get everyone to subscribe, get everyone to get onto this Discord channel, because I do a lot of answering questions on Discord as well. I don't know if you've noticed, in the Physics Q&A channel, ask a question, get an answer. Sometimes it takes a while because I'm busy, but drop a question off and it works. And you get an answer. And everyone can answer things as well. I'm going to go. Thank you very much. I'm going to mark a few people who are regular attenders now, so you get access to even more goodies. But I've spoken enough, so I'm going to stop. Have a good night, everyone, and I'll see you next week.